I made a pump that defies gravity. This video is not in reverse. This is called the tubeless siphon effect. This tube is sucking up the liquid, and this tube is putting it back in after it goes through this peristaltic pump. I can lift it way above the surface and it just keeps pumping like normal. How is this possible? The reason this is happening is because I'm using a special liquid here. It's called polyethylene glycol. This liquid was made famous for its self-siphoning effect, where if you have a jar full of it and start pouring it, it'll siphon itself out of the jar and empty the whole thing. Okay, watch it just kind of disappear out of the cup. So I barely tilt it, I leave it at the same angle, and it just drains it. But there are so many other cool things that this fluid can do. So let's dive into what this fluid actually is and see all the gravity-defying acts it can perform. Polyethylene glycol is used in almost every industry. Maybe the most well-known example is that it's the main ingredient in Miralax, which is a laxative. But it's also used in moisturizers, soap, shampoo, toothpaste, food additives, and even vaccines. The reason it's so versatile is because it's a polymer. So if you have one unit, it's just called ethylene glycol. This is what antifreeze is made of. But these ethylene glycol units can hook together to make chains that can get longer and longer indefinitely. In Miralax, on average, the chains have about 54 units of ethylene glycol each. The longer these chains get, the more peculiar the fluid behaves when you mix it with water. These long molecules get all tangled up with each other, and they also retain the water molecules in between each other. So you get a slippery coating on everything. You can imagine why this is a good laxative. But these chains are only 54 units long. What if we made chains that are much longer, like 16,000 units long? That's what I have here. This is polyethylene glycol with a molecular weight of over 1 million grams per mole. When the molecule is that large, it gets some weird properties. It starts to act like a tangled mess of elastic spaghetti and gets all tangled with its neighbors. So when you try to pour it out of a cup, it acts like you're pouring a chain out of the cup, and it takes the rest of the fluid with it. So now we can start to understand how this pump is working. It's like it's sucking up long spaghetti noodles, so it can rise above the surface of the fluid and it'll still suck it in. But these molecules aren't so long that one end is up in the tube and the other is down on the surface. Each molecule is very long for a molecule, but still only about 4 microns or less in length. So that means that we aren't just pulling up on a chain. But the reason it can get sucked up so high is that all these chains are getting tangled together, and they're slightly attracted to each other in the water around them. This attraction is really strong. For example, let's compare this to trying to lift up or suck up tangled spaghetti noodles again. Me being able to lift the PEG up just 5 centimeters is like being able to lift tangled spaghetti over 3,000 meters high. Definitely some very non-Newtonian flow happening here. Non-Newtonian means that the viscosity of the fluid changes depending on the shear force. For this solution of PEG, it's shear-thinning, meaning that it becomes less thick the more shear force you apply. This is because when you add a shear force, it straightens out all the molecules so they can flow past each other easier. So for our flowing liquid, it's almost like it makes its own tube. On the inner walls of the tube, the shear rate is high, so the liquid near the wall has low viscosity. But the liquid outside the tube diameter still has higher viscosity. So the thinner fluid slides right up into the tube through the outer shell that has higher viscosity. Even when you lift it above the surface of the liquid, the more viscous outer shell is being carried up and suspended by the faster moving inner shell. In fact, you can see how the outer shell of liquid can even have fluid flowing down in the opposite direction if it gets too big of a diameter. But this isn't even the coolest thing that happens with this liquid. This odd response to shear force creates another very neat effect called the Weissenberg effect. Normally, if you spin a rod in a liquid, the liquid that sticks to the rod gets thrown off of it due to centrifugal force. So this is just regular water. Watch how it moves away from the stick. But not this fluid, it actually starts to climb it. This is so cool. Look at that layer of liquid that just stays around the pull. Now if you look up why the Weissenberg effect happens, you're going to get hit with a lot of fluid dynamics equations that are giving the math behind it, but don't really explain the reason behind it. So without any math, let me try to explain to you the reason why this happens, why something could climb a pole like this. But before I show you this, if you're ever feeling like you're covered in PEG and just slipping through life, then let me tell you about our sponsor, BetterHelp. BetterHelp is the world's largest therapy service, and it's 100% online. With BetterHelp, you can tap into a network of over 30,000 licensed and experienced therapists who can help you with a wide range of issues. To get started, you just answer a few questions about your needs and preferences in therapy. That way, BetterHelp can match you with the right therapist from their network. Then you can talk to your therapist however you feel comfortable, whether it's via messaging, phone, or video call. And you can message your therapist in the app or online anytime and schedule a live session when it's convenient for you. If your therapist isn't the right fit for you for any reason, you can switch to a new therapist at no additional charge. With BetterHelp, you get the same professionalism and quality you expect from in-office therapy, but with a therapist who's custom picked for you, more scheduling flexibility, and at a more affordable price. So get 10% off your first month at betterhelp.com/actionlab, or you can click the link in the description. And thanks for BetterHelp for sponsoring this video. Now let's get back to our experiment. You can think of these molecules like little elastic bands. As you spin the stick near them, the elastic bands align in the streamlines. This means they get stretched in the direction that the stick is moving, but they're tangled with their neighboring molecules in different layers moving away from the stick. So those neighboring molecules get pulled toward the stretched elastic band closer to the stick. The closer to the rod, the stronger it pulls its neighbor toward the rod. You can see this same effect if I spin this stick on a stretched rubber sheet. So you can imagine a layer of this fluid like a stretched rubber sheet. If I spin this stick on the rubber sheet gets pulled up the rod. The reason it moves up is because it's pulling mass toward it, and the only way it can go is up. So it's like we have a liquid elastic that stretches and pulls on its neighboring fluid layers. What's really neat is that you can see this effect even when there's no rod. Watch what happens with regular water when I put it on a stir plate. The water moves away from it and makes an indent. But now watch what happens with the polyethylene glycol. You can literally see it bulge up and above the surface. Even with no stick to climb, it tries to climb towards the spinning. If I just stir the PEG, it'll bulge at the center and climb to the spot where the fluid is moving the fastest. Whereas if we just use water, it'll do the opposite and move away from it. This is because for regular Newtonian fluids like water, they aren't elastic, so there are no forces pulling on each other in the same plane when you move the liquid. But with a non-Newtonian fluid, there is. They'll keep moving up until the force of gravity overcomes the elastic force pulling them up. The effect is actually really common. It's the same reason why if you've ever made dough in a mixer, your dough always climbs the mixing paddle. It's due to these unequal normal stresses that are pulling the surrounding layers toward the stretched layers. This happens whenever you have big, long molecules. So if you get a really elastic, long polymer, then you can even see this effect even stronger. For example, this is just some regular homemade slime. It's tempting to think it's just climbing the pole similar to a corkscrew effect, but if I just stick a rod in the slime sideways and turn it, it'll climb both sides of the rod out sideways. So many cool things happen when liquids start having solid properties like stretching. The lines start to get blurred between something acting like a solid and a liquid. In fact, there's a specific number used in fluid mechanics to help you quantitatively describe how much something acts like a solid versus a liquid. This number is called the Deborah number. The Deborah number is the ratio of the time it takes for a material to adjust to the applied stresses and the characteristic time scale of an experiment. At high Deborah numbers, the fluid acts like a solid. At low Deborah numbers, the fluid acts like a liquid. What's interesting is that this number was named after the prophetess in the Bible named Deborah, who said the mountains flowed before the Lord. Because at the long time scales, everything starts to flow like a liquid. That's how you have straight rock layers that look bent over time. So in a world where boundaries are often clear-cut, these materials help remind us that nature operates on a spectrum and blurs the lines between states of matter. And thanks for watching another episode of the Action Lab, and we'll see you next time.